to the talk. I'll be talking about model-guided fuzzing of distributed systems and specifically how we're going to use TLA plus models here. This is joint work with Ige Barkai, Burju and Rupak. Before we get into the TLA plus stuff, maybe a bit of introduction and a precursor to just traditional testing. In the normal testing world, you have a program and the goal is to find bugs in the program. So you have an input space and you draw randomly from this input space and you feed it to the program. And the goal, you do this many times, and the goal is to, as I said, find a particular input that will give you a bug. Now you can improve this process, which is what they would call guided software testing. Instead of just randomly giving the input, you get some coverage information on the program. It can be line coverage or branch coverage, and use this coverage information as feedback to generate more inputs. And again, you do this many times to find bugs in the program. This is the traditional basic fuzzing loop. Now, if you want to adapt this loop to distributed systems, there are some challenges. First, you don't have one, you have many programs. Then if you want to do guided testing on distributed systems, it's not clear what is the input or what is the coverage. And the goal of this talk is to show how we define the input and also to show that you can use a TLA plus model as coverage to test distributed programs. Before we get into it, some motivation which might not be necessary for this audience. There have been many protocols, and these protocols have been implemented, and the implementations are generally buggy. They lead to large downtimes. There have been a bunch of examples over the years. My most interesting one is the 6-hour outage in Cloudflare because of a Byzantine failure in the Raft protocol. So we need to make sure that implementations are correct, and we need to test for these implementations given a protocol specification. And there has been a lot of existing work doing this. Popularly, there's Jepsen, which is a randomized tool. It runs the whole system end to end and simulates network failures randomly and tries to find violations and linearizability or serializability of the database. Then there's more work that comes from the former methods backgrounds, which tries to give probabilistic guarantees whether you have seen certain types of bugs or not. And this is PCT and PCTCP. And then there are frameworks that incorporate all these different algorithms, ones like Coyote, and also come up with reinforcement learning guided testing algorithms, which have been also quite successful. And more recently, there has been one particular work of interest for this talk, which is Mocket. It's a model-based testing tool, and the goal of Mocket was to generate tests from TLA plus model and use these tests to run them on the implementation and check if the implementation is correct. I'll be going more into what we do different from Mocket. Again, a bit of TLA plus overview, maybe not necessary for this audience. Here we have a simple model of a counter that can be incremented or decremented. Here's a state. Here's the actions that allow you to increment and decrement. And then there are the transition rules that you define for each action, how the state should transition. And for this talk, I will be using a Raft protocol, and I'll walk you through the Raft TLA plus model as well, along with the protocol. Most of you might already be familiar with this. So Raft is a distributed message passing protocol. It solves for consensus. Basically, if you have 3 nodes, you want all of them to agree on the value, in this case represented through R1. And it wants to do this under the presence of crashes, so a node can just fail, stop responding. And the protocol proceeds in 2 phases. There's a leader election phase and a leader application phase. So let's get into it. You have 3 processes, and this is the initial state. I'm only taking a part of it just to represent. And later give you some highlights about this snapshot of the state, but the actual protocol contains a lot more information on the state of each process. So you have in the initial leader election phase, the process says it wants to be the leader, so it will send a request vote message. There is a corresponding action to that, and then other processes respond with either a yes or a no, and there's another action for that, and eventually a process becomes a leader. So this concludes the leader election phase, and then you have the leader replication phase where the elected leader replicates entries through append entries messages. So on the left you have the state, and on the right you have what would look like a global transition of the protocol. And then there are the relations. So together this is a snapshot of the whole TLA plus model for Raft. The actual model contains more information. And what does the model allow us to do? It allows us to go through these different states where between the states the transitions are annotated by the actions. In this case, the actions are receiving certain messages or timing out and so on. Now you can ask, as Mocket have already demonstrated, why don't we just enumerate all possible executions from this model and run them on the protocol? Why do we need this fuzzing loop where we take coverage information and what is even coverage? Now there are some limitations and drawbacks with this model. One, as we all know, there are way too many executions, so there's an explosion. It's quite unrealistic to be able to enumerate all possible executions, and we still don't know if there's a way to nicely partition the state space so that you can cover all possible executions. And more than that, even if you had all possible executions, to be able to run them on the implementation, it requires a lot of effort. You need to instrument the implementation to be able to control exactly when a message is delivered and what code runs after the message is delivered, where to stop, and so on. And more than that, the model also ignores sometimes some of the optimizations in the code, and so these parts may not be even tested. For example, there are snapshots which the model sometimes does not include, or heartbeat messages, and so on. That brings us to our approach, ModelFuzz. So we randomly generate inputs, and these inputs are what we would call test cases. You run them on the implementation, and then you in parallel also run them on the model. So here's a picture of what happens, and then we'll make this picture more detailed as we go forward and eventually complete it. So you have test cases, you're going to execute them on the model and then collect some actions and run them again on the model checker, get information on what model states you saw, use that information to generate more test cases. And yeah, here the magic lies inside these mutations. We have some simple ones, and I'll go through them later on. Now, what does it mean to run a test case on a scheduler? But before that, what does a test case even contain, or what is it made of? So we define a test case as a sequence of scheduling choices. So for example, here you can say deliver 5 messages to this process, deliver 3 messages to another, crash a process, start a process, and so on. So these are what we would call our test cases. Now you can ask, why not just generate test cases as all those messages that could be delivered in what order you want? The problem with this is you cannot just randomly generate these test cases because not all of them are valid. For example, a non-leader cannot be sending a message that is designated only to be sent by the leader. And how do we run these inputs? So you control all the messages. So if we say deliver 5 messages, you have a central node that receives all the messages, and it can pick and deliver the messages per process. So in this case, it will deliver 5 messages to P1, 3 to P2, crash a process, and start it, and so on. As I said, you can easily generate these inputs randomly, and it does not require a lot of instrumentation to be able to run these inputs. You just need to control which messages are delivered, how, and this is usually built by instrumenting only the transport layer of these protocol implementations. And then you also need to be able to control when you can start or stop a process. And more than that, it's easy to define mutations on these inputs so that you can randomly generate new inputs and they lead you to new states. We'll go more into that later on. Now, along with running the input, we collect some event information that happens inside the process. So if you say deliver 5 messages, we also collect exactly which 5 messages did we deliver. Was it a request vote? Was it append entries and so on? And then, also starting and stopping processes. And if a node became a leader, this is an event information. So this is the set of execution events that corresponds to an input trace. Need not be one-to-one, but it's an abstraction that we are willing to work with and has shown to be good enough. So now we saw how to execute the input and how to get out events by executing this input. And with these inputs, we want to be able to simulate them on the model. So first, let me show you what we do on the model and then connect how we use the events that we collected to be able to do this simulation. What do we want with the simulation? We want to be able to capture which are the states that this particular trace went through as we executed on the model. So we want to simulate this. But there are some challenges to simulating it, especially with TLA+. We want this to be very fast. We don't want it to be time consuming. And the model checker should be able to quickly enumerate all possible actions, pick the one that corresponds to the trace, event trace that we observed, and go to the next state and so on. And we don't want to execute actions that are irrelevant to the trace. To recall, this is all the actions that we saw for TLA plus model for Raft. And as you can see here, it just says for all, there is an action that says receive a message for all possible messages. This is a non-deterministic action. The message is not exactly defined. So if we want to simulate a trace and we observe an event that says a message was delivered, you have to pick this particular receive action, and then among all the possible states, pick the corresponding state that corresponds to the message and do this many times. So this is quickly blowing up the asymptotic complexity of being able to simulate traces. But it requires less space. So this was not fast enough for us and it was too expensive. It was consuming a lot of time. So what we did is we refined the model. We said, okay, we're going to fix how many possible terms, how many indexes are possible, and then define actions per messages. That way, all possible actions can be easily enumerated. This can be stored in memory and is a one-time process. And now picking the action corresponding to a message is just going through this list and finding the right action immediately. You don't have to go through all possible states and find the corresponding state that you are interested in. It's linear, asymptotically better, although it needs a lot more space. Okay, so we saw how to simulate actions on the model, and we saw how to get events out of the execution. Now, to connect events to actions, it's a simple mapper. This mapper is specific to the implementation. And here it's possible to also introduce abstractions of the events. So you only want to abstract away, you want to capture only specific events that are interesting for the model and drop the remaining. So you can add that abstraction here. For example, you can ignore heartbeat messages, which are not in the model, but something that the implementation spits out when it runs a trace. And also this mapping is very specific to each implementation because the data structures that are used to capture the events might be specific to the implementation, although you can generalize it to each protocol. Okay, so coming back to the full picture, we saw how to generate test cases, run them on the implementation, get events, simulate them on the model, and capture the coverage information. Now the only part remaining is how do we use this coverage information to generate more test cases. That's the mutation part. As I said, a bit of magic here. And in our case, we choose to do swapping mutations. What does that mean? We swap scheduling choices. So if you're saying deliver 5 to P1 followed by 3 to P2, you're going to swap them and say deliver 2 to P2 and then 5 to P1. You can also swap which processes you crash. You can swap how many messages you deliver. And in our case, doing all these swaps gave us good coverage information. But in our initial runs, we really did not see a lot of improvement over just pure random exploration. And we couldn't beat random. And what we found out was there was an abstraction that we were missing that is specific to Raft. So you can have term numbers in Raft. So a term denotes which node has been elected as leader, and that leader is going to replicate it to all other processes until a new term occurs. So what random was doing is it was just skipping terms. So it was getting to new states, although these are not interesting. So we needed to abstract this away. For that, we bounded the number of possible terms, and we only consider states that are different only if they differ in term numbers. So if you have the same term numbers, if you have two states that are different only in the term numbers, then we collapse these two states to one. So that allows us to explore actually unique and interesting states. And this abstraction was implemented inside the model checker, and this is also something pluggable and specific to the implementation. Once we did this, we got a lot of interesting results. So we ran our fuzzer on a micro branch park implemented in the Coyote framework. Then we tested etcd, which is a popular key value store written in Golang, about 1,000 lines of code. And then we tested Redis Raft, which is also another key value store written in C. And we, across the board, we saw that doing ModelFuzz or fuzzing using the model as coverage gave us better coverage over the model than other notions of coverage, such as line or trace. And there's a bit more that we also gained. We saw that using the model as coverage does not degrade the coverage of other notions such as line. So line coverage we saw was something that saturated very quickly. And it was hard to gain any coverage information to be able to get to new states. And we also saw that trace coverage, basically, if you took two input traces and treated them as distinct and used this guidance measure, it was too fine. So we were seeing a lot of new traces, but not getting to new states in the model. And the other thing is, as I said, using the model as coverage did not degrade. So we got good branch coverage using ModelFuzz compared to, say, just guiding using branch coverage or line coverage and so on. So it was a win-win in some sense. And in terms of bugs, we found one new bug in etcd, and we found two known bugs also reported by other tools, and we found 12 new bugs in Redis Raft. We put them on GitHub. They are yet to be worked on. And more than that, we found these bugs statistically faster. So we took we ran fuzzing for 20 times, each time for 24 hours. And we measured for each bug when did we first hit it. And we show that we are better than using other guidance measures. And we are significantly better, especially if the bug is rare. So if we only found the bug once in all these 20 times, we were doing them much faster than other approaches. Where does the work fit in overall? This is something that puts it into perspective and gives us directions to go forward. There's been a lot of work on modeling using P and these actor runtimes or IV and proof-based techniques. or Daphne and other verification languages, and to this community very popularly using TLA plus models. And we want to leverage the modeling efforts that have been put in to actually test the implementation. So this is the main problem that our work here is trying to address. You can plug in a different model and take any implementation and use the basic idea that using a model as coverage actually helps you test the implementation. But there are some limitations to our work that we hope to be able to address in future. There's a lot of effort that needs to be spent to be able to use model guided fuzzing. You want to write the mapper, you want to be able to instrument, and more than that, you need to have a TLA plus model that you can work with. And the other thing we observed is that the whole approach is quite sensitive to abstractions. It does not work well if you don't have the right abstraction, and figuring this out itself took a lot of time and effort. If you're too fine-grained, you gain too much information and you don't see new states. If you're too coarse-grained, again, there is not enough information and you don't see new states. So going forward, we want to be able to effectively evaluate different mutation strategies. In our case, it was just ad hoc. We were trying different things to see what works. A more systematic evaluation would be something that is worth doing in the low-hanging fruit. And we want to be able to do better means of mutating something using machine learning or other learning-based approaches to be able to mutate the inputs so that we know exactly what new trace will give us a new state. This is something that can be interesting to explore, and what works, what doesn't. And this whole mapping effort, although currently it's manual, can be fully automated because you know what events implementations are going to spit out, and you know exactly what actions, and figuring out the data structure and being able to map this should be automatic for a protocol for a given implementation. So this is another low-hanging fruit that we can pick up on. The other thing that comes for free with this work is the conformance checking, and this community might already be familiar. There was a recent work that explicitly addressed conformance checking for etcd using TLA plus models, and I will leave a reference here for that. Thank you so much, and I'm happy to take questions.